So we have our data. Of the 60 printed circuit boards, 32 of them had 0 defects, 15 of them had 1 defect, 9 of them had 2 defects, and so on and so forth. So a random quantity here is the number of defects per circuit board. But that fits the description of the number of occurrences per time frame or space frame that was consistent with the definition of a random variable for a random variable x that followed a Poisson distribution. The question is asking whether this x here actually follows a Poisson distribution with a lambda of 0.75. So our null hypothesis versus our alternate, just like in question number 2 and question number 1, guys, the null hypothesis is that x came from some, distribution. In the first question, our null hypothesis was that the x, which was the roll of the die or the result of a roll of the die, came from a uniform distribution. In the second one, there was no particular name for that distribution, but it was asking whether probability of age group 1, 2, 3, and 4 were equal to the prescribed 30%, 40%, 20%, and 10%. Here, our null hypothesis is that data came from a Poisson distribution. The alternate is that data didn't come from a Poisson distribution. So what we're going to do is we're going to compute the expected frequencies, assuming that H null is true. So had these numbers come from, or had the number of defects per circuit board come from a Poisson distribution random variable, the probability that we will get 0 defects will follow the Poisson distribution formula, which is e to the minus lambda to the power of x divided by x factorial. So e to the minus 0.75 times 0.75 to the power of 0 divided by 0 factorial, and we get 0.472. And I'm going to fast forward here, guys, and solve all of these for you. Here we go. So again, had x followed a Poisson distribution with a lambda of 0.75, the probabilities of getting 0 defect, 1 defect, 2 defect, 3 defects would be these here. Using these probabilities, if I sample 60 circuit boards, I would expect to see NP1, or if I calculate that, 28.32 defects out of 60. Had these number of defects followed a Poisson distribution, I would expect to see NP2, which is 21.24 number of defects. And same thing for E3, 7.98, and E4, which is NP4, or 1.99. And we're going to compare these against our observed frequencies. And let's just write the observed frequencies here, just to remind everyone. So the observed frequencies where are you, my observed frequencies? 32, 15, and 32, 15, 9, and 4. And these are my observed. 01, 02, 03, and 04. And just like in question number 1 and question number 2, we're going to compute chi-squared test statistic But one adjustment we have to make is, as a rule, this is how whoever made the chi-square test statistic made, is that if you get an expected frequency that's less than 4, what you do is you combine these two categories into one. Okay. So the combined expected frequencies now would look something like this. So I'm going to change colors here. The expected frequency for E1 doesn't change. O1 doesn't change. E2 becomes 21.24. That doesn't change. Observed 2 is 15. But the combined frequency that I'm going to call E3, 4 will be 7.98 plus 1.89. If I add those up, what do I get? I get 9.96. And I'm also going to combine the observed frequencies for 3 and 4, and that's 13. And using these numbers, I'm going to calculate the chi-squared observed, and that's the sum of how much the observed frequencies deviates from the expected. The more deviance we have, the more evidence we have against the null, or against the fact that, against the hypothesis that x came from a Poisson distribution. So I've computed this number for you, 3.239. Okay. Let's draw a chi-squared distribution and go look for a critical value. We're told to test this at alpha equals to 5%. So we're looking for a chi-squared that makes that equal to 5%. So chi-squared critical, which here is going to be chi-squared sub 0.05, and the degrees of freedom here is actually the number of categories after combining the third and the fourth categories. So it's going to be, our k is going to be 3, and we're going to take away 1 from it, yielding us 2 degrees of freedom. Look that up and let's see what we get. I'm going to go bring it up from the chi-squared table. And I get a value of 3.841. Our test statistic, 3.239, is not deep enough in the rejection region. We therefore fail to reject. And conclude that the data doesn't suggest, or there's insufficient data to suggest, that the number of defects follow a Poisson distribution.